Okay, we're going to start with our second talk. So Georg and Demian are going to tell us a little bit about how Firebolt met Iceberg. So I'm very excited already, and we'll hand it over to you folks.
If you want to
Thank you for the introduction. So, yeah, I'm really happy to speak in front of such a big audience. Thank you for the Munich Data Geeks for inviting us. Also, thank you for giving a great talk about Lakekeeper. And today, my colleague Demian and I, Demian, he did a PhD in the past at KIT and now joined Firebolt as a software engineer. I myself, I've been located in Munich for quite a while, did my bachelor's and master's at TU Munich, and also joined Firebolt as a software engineer. And we both going to tell you the story today of like what happens when Firebolt meets Iceberg. Also, I'm going to start with quick questions. So the first question is like, who of you in the audience has had any touch point with a large-scale data system such as BigQuery, Redshift, Databricks, like anything? Who has ever like used it or maybe even developed some parts of it? Okay. Large part of the audience. So then my next question is like, who of you has ever built an unresponsive application? And sadly, I also have to raise my hand here. First application, run analytics queries in Postgres. Didn't work so well. So what I learned back then, and also what we as Firebolt, what we stand for, is on the next slide. Analyzing data at low latency cannot be taken for granted. It's very easy to build something that doesn't scale. And everyone who has ever built any application probably felt some pain at some point. So what we want to do today is we want to explain to you what Firebolt is, why it's great, and also why we think we should be on the major query engine slide the next time Christian's going to give his talk, and how we solve our problems. So the next slide. So you might ask, like, when can you use Firebolt as a product? And what we think, both Demian and I, we discussed this before his talk, we think, or we are convinced, Firebolt is built for analytical queries. So we are all about analytics on large amounts of data. And then what we really optimize for is repeated query patterns. So many of our customers, they run user-facing applications on top of Firebolt. For example, we have customers running a comparison portal. They are comparing different products, so their users are entering like a filter. The filter is maybe different, a little bit different every time, but the query is basically the same. So for those repeated query patterns, we optimize our system. And then what's also important about Firebolt is that we want to serve many queries concurrently. And the last point is, oftentimes when running on large amounts of data, in the end, you only need small amounts to actually answer your query. So we think one big part of being really fast is just not doing too much and only scaling as much as you need. So this is when Firebolt helps. And so you might wonder, like, how do we actually help? So building for analytical queries means you need a columnar query engine. Also, as Christian mentioned, so if you couple storage and compute in the same component, it's terrible, it doesn't scale. We learned that like decades ago, or maybe a few years ago. And then for the next point, like repeated query patterns, we built a very cool new project, which also Demian worked on, is the sub-result cache. So we can reuse parts of a previously computed query to answer the next query, which is really helpful for repeated query patterns. And then handling concurrent queries, the answer is elasticity. Elasticity has many dimensions. So many of you probably learned that at one point running on a single compute node, like a single server, is not enough anymore. So you need to scale, usually you need to scale out. So you need to use multiple servers at the same time to compute your query. What you can also do is you can vary the size of the actual server. So you can go from a very small server, which might be nice for a very small use case, because it's cheap, up to a very big server, like the biggest instances on AWS, for example. And then what we also did is, not only can we scale out and scale up, we can also use multiple clusters at the same time. So we have like 4 nodes running and then another 3 nodes, and you shoot queries against Firebolt, and in the background, we route them to the available cluster all the time, and you get ACID compliant results. So this is how we solved, or how we tried to solve, many concurrency problems. And then small slices of big data sets. The answer to that is indexing and pruning. Indexing is also mentioned on a repeated query patterns. But basically, if you pre-compute part of your query, it will help you to answer the query really fast. And then the other thing was only scan as much as you really need. This is where pruning is powerful. Okay, and now the question like why does it even help if you are really fast? I mean, you can serve an application with much lower latency than you can do with other systems. So here is a chart that shows a bunch of our customer queries. So of course, I mean, we build for our customers. We try to build in a very low latency manner. If we run the same queries in other systems, the queries, like the latency skyrockets, and especially also the cost that you have to pay to get the latency down. So usually you can scale up your system, except BigQuery is different. Usually you can use different sizes of the system to get lower latency. But the thing is, in the end, what matters is how much you have to pay for it. And this is why we think low latency serving is really important, because it allows us to give you what you need to build a responsive application at low cost. All right, so this is more general about Firebolt. And so we call ourselves the next gen cloud data warehouse. And we think cloud data warehousing is, like if it's decoupled, of course, computer storage, is far from being that. We also think it's the best thing you can do for many use cases. But for some use cases, we also think Iceberg is a game changer. Because what Iceberg allows is to decouple the writing system from the reading system, for example. We had talks previously with other companies like Rising Wave, which you might have heard of. They are solely focused on writing Iceberg tables efficiently, generating good per K files, because having good per K files allows you to then read this data efficiently again. And we can sing a song about this as we implement this part of the system. So a quick one-on-one. Iceberg, I mean, we heard about it previously, so I'm going to do it really quickly. So, I mean, you might ask, why can't I just dump a per K file on S3? The answer is, we need schema evolution. Tables can change. You can add and drop columns all the time. This will happen. Also, it can allow you to use functionality like time travel. Read query, like read stale data, basically. Say you want to read the data from like 2 hours ago. And it allows you to have ACID compliant transactions, because the data always needs to come from somewhere. And this somewhere should behave in a consistent manner when reading the data again. And then how it works, or how we, as implementers of the read path, needed to think about this. It's basically hierarchical files stored anywhere, maybe S3, for example. And those files, they point you to the next file, and the next file, and at some point you can find the data files, which are then stored in per K. And those we want to read very fast. And as I said, it's great for us, because we think this allows us now to not only bring customers onto our managed platform, but also show everyone here who has an Iceberg table lying around really easily. Just point Firebolt to your Iceberg table, and you can see the really fast and good performance without any migration pain. So I want to continue by explaining how we think about low latency problems and why we think it's hard. So at the bottom of all this is usually object storage. If you have large amounts of data, you will store it in GCS or GCP or S3 or maybe Azure. And this object storage is connected via, you can access it with HTTP connections to load the data from the object storage to your query engine, which is usually running in an EC2 instance, for example. And moving this data around has some latency. So it takes some time for you to request the data and get the answer. What you can see here is plots from a paper published by a former PhD that advised me for my bachelor thesis, actually. And he analyzed the latency of S3 depending on different block sizes, because this actually matters. if you request very small amounts of data, like 1 kilobyte, you have faster latency than if you request, or lower latency than if you request a 1 megabyte chunk. The problem is if you request small amounts of data all the time, you will never be able to saturate the full network bandwidth of your EC2 instance, which can be up to, I think by now, 400 gigabits per second on a single EC2 instance. Maybe it's not released yet, but enough. So what we needed to find here, we needed to find the right size in which we want to request data to achieve both the minimum latency as well as, secondly, we want to saturate the full network bandwidth because we think network bandwidth is the new bottleneck. So what does this mean for Iceberg? You saw that we chose some block size. We chose something around a megabyte or 2, and this has around 100 millisecond latency. So what happens now if you request the hierarchical files, first the metadata file and then other ever files, I don't remember all the names, you add up all the latencies. And then in the end, you scan the data files, which can be only maybe megabyte, but still it takes you half a second to answer any query if you always get the data from S3. So this is where we stood and we thought, okay, it's not acceptable for us because this latency is too high. Our customers run queries that should be answered in around like 10 milliseconds instead. So now I want to hand it over to Demian, my colleague, who will show you what we actually did to solve this.
All right. So thank you, Georg. So right, it's demo time. Actually, like this in the picture here is a screenshot of our managed SaaS offering, but today we want to actually show you our new offering called Firewall Core. This is a free offering. It's something you can simply run on your local machine using Docker, and it's exactly what I'm going to do today. So what I'm going to show you now is actually running here on my MacBook. So let's go over here. So this is the command I used to run this. It's going to look very similar to this for you in a week when we actually launch this. So let's start the Firewall server. It's up now. Cool. We can run Docker PS and see that there's a Firewall Core running Data Geeks demo. Okay, so let's see what we can do with this. I have prepared a small function. It just sends a curl request to my locally running Firewall Core server. And this is how you query a Iceberg table in Firewall. So we picked a table schema that's hopefully very familiar to most of you. It's the TPCH schema. So here we're reading from the orders table in TPCH. We're just selecting a couple of columns so it doesn't overload the screen. So we use a function called reads_iceberg. This is a table valued function, if you're familiar with these. So it looks like a normal scalar function that you would normally execute on a single row of your table. But what a table valued function actually does, it creates a whole table. And then we can do, well, anything you can do with a normal SQL table. So we're selecting these 3 columns. We're limiting it to 10 results. So the screen doesn't get overloaded. And what we will actually see, okay, that took like 1.58 seconds. That's not very low latency. And the reason is that exactly the image that Georg showed you just before, right? We have all these levels of requests that we need to do, which add up a lot. I think in your slide you said it's 0.5 seconds. That might be true when you're actually running this where the data also is. But the data, I think you can see it here in the path. It's in US East 1. My laptop is in Munich, Germany. So we're not quite at 0.5 seconds. We're actually at 1.6 seconds. But actually, when I run this query again, it's going to be super fast. And we're going to talk about how this works in a second. It is not just result caching. I didn't just get the result of this and return it again. I also have a slightly more complicated query, hopefully here. Yes, okay, so here we are basically doing a much more complicated query. We're reading orders, customers, and nation from TPCH. We're joining them on the customer key and the nation key, and then we are computing some statistics here, the sum of total order price of each nation and the count of these. If I run this again, it's again going to take a while because, again, we need to request all these metadata files from S3 first before then downloading the actual data, because that's how long it takes to actually get the paths to these files that we want to download. And again, if I run this again, and this time I can actually show you that I'm not cheating and doing a result cache. I think I have it prepared somewhere with, oh no, that's the wrong query. Let me, right. So this is basically almost the same query. I just added a filter to the order date. So now I just want to get the statistics for each nation, but filtered only for these orders that happened after January 1st of 1998. And this, still super fast, 40 milliseconds, not even. So let's see how we can actually do this on Iceberg, because Georg just said we can't get below 0.5 seconds. Seems like that's not true. So today, there are lots of things going into that. We're going to talk about two of these things that Georg and I know the most about. One is how we use sub-result caching for Iceberg, because there are some tweaks for Iceberg that really help here. And then once we get to the part where we actually have the data files in hand, how do we efficiently read those data files? So this is the table that I just showed you, just without the whole read Iceberg TVF stuff. That's just a bit too bloaty to look at here. So we have 3 tables that we're scanning from. We are summing them, we're counting them, and grouping them by all, which is just fancy syntax for grouping by nation name. All right, so on the left here, I hope this is something most of you can at least somewhat, understand what this means. It is a graph that depicts how this query is executed in our engine. So basically, we have down here a scan of the customer table and a scan of the nation table. And then there's a join operator, which creates the result of the join of customers and nations. And then on the left here, we have another scan that scans the order table, then joins the result of that scan with the result of the other join. And then in the end, we do an aggregation. OK, so now let's see what can we do here in terms of sub-result caching, because this can get quite large, and we would like to, if someone comes in later and sends a very similar query, we would like to reuse parts of that. And we have right now 2 different mechanisms for this in Firebolt, and we're going to see in a second how this plays into Iceberg. But these 2 are caching the hash tables that are built for joins, as well as a special caching operator, which is called the maybe cache operator. It's called maybe cache because the optimizer adds it anywhere in the plan, and then the runtime decides whether it actually wants to cache based on how large is the result. Is it even worth caching this? So what happens here is we execute our query, we scan the nation table here. In this image, when something is on the right side of a join, it means we build a hash table for it. If it's on the left side of a join, it means we probe the hash table against it. So in this case, we scan the nation table, we build a hash table for it, and then we write this hash table to a cache, which we call the fire cache, because everything needs to have fire in the name at Firebolt, obviously. And the same happens here for the other join. So the result of this join gets streamed to the next join operator. We again build a hash table for it to join it against customers and restore that in that hash table in our cache as well. And then in the end here, this is a very simple case of where you could insert a maybe cache operator at the very top, so it caches your result of your query. And so this will also write everything that this operator produces, which is just what the operator below it produces, the aggregation, into the file cache. Okay, so now when the next query comes in, we check in our maybe cache operator, have I seen this entire sub-plan? So everything down here, have I seen this before? And has the table below it changed? Because obviously we need to take transactions into account. So when the base table changed, we can't just return an old result. Obviously that works as well. And in this case, we say, yes, we have seen this before. We check in the cache, we find a cache hit, and just immediately return the result. And nothing below that is even executed. Okay, that's a bit boring. It's just a fancy result cache. So let's look at something a bit more interesting. Let's say we change our queries. This is actually the second query that I just showed you, where we, on the left side here, add a filter for the order date. So this is, this is no longer the same query as before, right? So this caching operator cannot return the result that it previously computed because we're executing a different query now. But actually this right side, the join of customers and nations, that never changed. So what we can do here is we can take the hash table that we built for this right side, retrieve it from the cache, and don't execute this entire right side of the query. Okay, so how does this play with Iceberg? Well, the first good news is, well, actually nothing I just said really cares about whether the data came from Iceberg or from Fireball's managed format. So everything we had to do here was basically teach it what Iceberg tables are and make it understand when Iceberg tables change so it doesn't return stale results, but that's all. But the more interesting part is where else this comes in. So, and for this, we need to look a bit more into how reading Iceberg tables works in Firebolt. And part of the equation here, which is what the query execution side of our engine sees, are two table-valued functions. One is called list Iceberg files, and one is called read from S3. So basically, from the metadata files, we get the list of all files that belong to this snapshot of your Iceberg table, and then we stream these into the read from S3 operator. We download the files from S3 and return the columns or the rows from your table. But this list Iceberg file is basically the part that had all these staggered 0.1 seconds in Georg's picture. So we would actually like to not do that. And the cool thing here is, well, we can just add one of these maybe cache operators in between here. Like list Iceberg files just returns a list of files. It's not that huge. So we can afford to just cache just the list of files in memory. So the next time we run a query on the orders table and it hasn't changed in between, we will just not execute this part. We will not do all these staggered 0.1 second reads. We will just retrieve that from the cache. So we actually can get below 0.5 seconds with this. And this is exactly what you just saw. Of course, there's more to this story, right? For example, this read from S3 operator also won't re-download the same files that it just downloaded from S3 again. It also actually has them cached on disk. You also need to do something about your metadata file where you look up, has my data changed? There's also some caching involved into this. So this is just one part of the picture here. Right, and with that, Georg is now going to show you basically what this read from S3 operator looks like.
Thank you, Damian. Right. So as Damian said, I was concerned with the read from S3 table-valued function. And what it does is it retrieves data from S3 or any other object storage and then hands it over and decodes the data and then offers the in-memory columns to our query engine. So while this might sound easy, I can tell you it wasn't. Also, I didn't build this all by myself, of course. We were a team doing this. I was mostly concerned as this came out with the control flow and with the fetcher. Everything else I was involved in the design, but didn't implement it myself. So our goal with this GAN architecture was that we can fully utilize our resources. And I said previously, what we want to optimize for is the network bandwidth. We think by now it's really, really hard to fully saturate the network bandwidth without hitting any other bottlenecks in the system, like CPU performance or main memory bandwidth. And what's the underlying problem of building a GAN architecture is the high latency of object storage. So for example, I mean, from Dina's laptop to US East 1, the latency was crazy high within the data center. It was the plots that I previously showed. But what's the problem here? So if you request, let's start with one end of the spectrum. You could request all your data, like terabytes of data, download them to your server from S3, and then do the computation. What happens if data grows? You run out of main memory. Doesn't work. I can tell you that. And then what's the other end of the spectrum is you request, for example, 2 MB of one file, process the data, hand it over to the query engine and generate the results. And then once this is done, you go back and get the next 2 MB chunk. And the problem with this is you always wait in between those 100 milliseconds roughly until you fetch your next block of data. Okay, so this is the underlying problem that we tried to solve, and we needed to both fetch data from S3 at the same time as doing the processing. We need to make sure that we never fetch too much data such that we run out of main memory, although like the query processing pipeline can take arbitrary amounts of main memory. So this is really, really hard. And the components we built to try to solve this problem, I get into some details in the next slide, but as a rough overview. So we'll start from the bottom. We could either fetch the data from an object storage, or, Dima mentioned this also, we need to cache it on a local SSD to avoid the excess latency for the data files. So we have the fetcher component. It's just responsible for issuing those GET requests, HTTP GET requests against S3, for example. And then handing the data blocks, which are here painted in gray, to the buffer manager. And then the disk manager, on the other hand, is responsible for writing data, which we want to cache, as well as retrieving the cache data from the SSD. And those two components are used by the buffer manager, so we call it. So the buffer manager component, it stores, or it basically manages all those individual blocks. It knows like to which file on S3 does this certain block belong to, on which offset, and so on, and it actually interacts with the fetcher and disk manager for this. And then up from the buffer manager, we actually have the control flow. The control flow is responsible for scheduling the right thing at the right time. So you either schedule something that issues a fetch or disk read requests, or you schedule something that decodes the data that was previously fetched, because it might be stored in Parquet file format. It might be stored in Avro file format, any file format, basically. And this needs to be decoded into our in-memory format. Okay, so this is a rough overview. And now on the next slide, you can find, not a lot of text, but you can find some of our ideas. And I want to explain to you why we think it solved the problem that it shows. So, we chunked the files. I mentioned this a couple of times. We chunked it like in fixed size blocks. And what it allows us is it allows us to fetch at full network bandwidth. Because it could be the case that a Parquet file has many row groups, if you're familiar with the format, and those row groups are tiny. If it has tiny row groups and you only fetch one row group at a time, you end up not utilizing your network bandwidth. So what we did is, in the background, we fetched the full 2 MB block and then shared it between multiple row groups, for example. Okay, that's the first point. The second point is, and everyone who's a C++ nerd here might be excited about this, we use coroutines. Woo! So coroutines are a really exciting feature by C++, and they're great because they allow you to stop your program at basically arbitrary points in your function, which looks like a sequential function, but it has those tiny keywords that tell it, okay, this request now may take some time, it may need to fetch data in the background, but it handles this stop and start of the execution transparently without you needing to write very complex code. And we needed this because the fixed size blocks, they caused us to read from non-contiguous buffers. So it now could be the case that one row group is really big, like 10 MB. And this row group is fetched in 2 MB blocks. And so we need to decode data, which is stored in non-contiguous buffers, into our in-memory format. And stopping at arbitrary locations in your code is really, really hard if you don't use coroutines. Yeah, we were really excited about this. And then the next point is caching. Caching has basically two reasons. One, already Damian mentioned, we need to cache to achieve very low latency. Second reason is, at some point, your network bandwidth is fully utilized. But you might be running queries over and over again, so we might have cached some of the data previously. So what is left besides the network bandwidth? It's the disk read bandwidth. And it's actually possible to read from both network as well as disk at the same time. And now you can use two different bandwidths, network bandwidth and disk bandwidth, and fully utilize them at the same time. And then the last point is a concept called the task families. I talked about row groups a bit, and not everyone in the audience might know what a row group is, but it chunks Parquet files into individual chunks of data that can be processed independently. So this means each row group can be decoded on an individual CPU core at the same time. And what our concept of task families, which span multiple tasks, allow us is to schedule those task families. So the control flow is responsible for scheduling the task families on CPU cores. And those task families comprise multiple tasks. One task is, for example, decoding one column. You also mentioned Parquet is a columnar file format, so it's very easy to decode columns at a time. If we only have one task family in the system, we could also use multiple cores to execute, to process this single task family. But the great thing is that each core can make progress individually without a lot of lock contention, because this really, really kills scaling to multi-core architectures well. Yeah, and with this, I hope both Dave and I could give you a bit of an understanding. First of all, what is Firebolt? We started with this. Then also why we think Iceberg is great. How we try to solve the problems with Iceberg. And also we hope we could convince you that we are really excited about the challenges that we need to solve. And we're happy to continue any discussions after this talk or in the open question session. Thank you so much.
Awesome. Thank you for the talk. Are there any questions?
Yeah, thank you for the talk. I'm afraid I didn't get everything.